Good morning, everyone. I hope everybody had a nice evening last night and a good night. Welcome to the welcome to the morning session of our conference. My name is Norbert Barszczewski, and I will have a pleasure to moderate the session. We have two speakers today. Our second speaker is virtual, so we'll facilitate the best we can. And our first speaker is Glen Tobiason. He's the president and CEO of InnoWaCon company. Glen has been a big supporter of our conference. I don't think you missed many, if any of them. So very warm welcome to Glen. Take it away.
So, good morning. Is this coming in clear? Very good. I had a great night here tonight. Very nice hotel. Gene and the whole crew did a great job. Thank you very much. InnoWaCon, my company, Innovative Waste Conversion Technologies, we're bringing technologies over from Germany. One is technology I'll be talking about right now here, and also some shredders and also some AD biological biogas technologies, also from Germany. We want to look at the organic content laden MSW to high methane content biogas and RDF. You know, is this viable? Is this SB 1383 compliant? I'm not going to go into SB 1383. The Californians know it very well. Everyone should know it. And I think all the other states are probably going to follow if I hear the trends out correctly. No? Good. To answer that question I had up front, I simply say yes, but why? Look at landfilling these days. Look at the capacities, what's out there right now. We don't have to talk about that too much. I know in the Northeast, where I am running my company from New Hampshire, Northeast, the New England states, it's a terrible situation. There's undercapacity. They're going to be bringing a lot of waste to Tunnel Hill landfill in Ohio and other places, which I don't know if that's reasonable anymore. Trying to site a new landfill anywhere, forget it. I think you all agree on that one. And the very high methane leakage, we talked about this in the last 2 days. It is now the third worst methane emitter. That's damn serious ecological consequences that we have to face. And you've been seeing it all in Northern California, Vancouver, all places all over the world. What's happening with our land? What's happening with our weather? What's happening with our environment? Maybe we can do something on a small scale, and I'm being a little political or philosophical here right now, but maybe we can do something on a small scale just to stop certain things. So I'm kind of asking, what can we do with the landfills right here? And that's not going to be a big talk today, but what can we do with the landfills? Knowing that the methane emissions are so terrible right now and what they come out of it, 86 times worse than CO2, as we heard, it really tells me we have to close out the landfills for anything that gases out. That's a big word. They did that, I know, in Germany, where I was living the last 36 years until July 4th last year. In 2005, they stopped landfilling or was no longer allowed to landfill any waste that would gas out, give off any emissions like that. Sandstones, inert materials, yes, that can be landfilled. It's quite a bit less than just MSW landfilling, and with complete methane capture as well. Look at also the waste hierarchy with landfilling. That's down at the bottom. That's the last resort. And one thing I have to ask is, you hear tipping fees, sometimes 30 bucks a ton, sometimes 50, all over the place. And then I have to ask the people, what is the total cost of ownership of that ton in your landfill, please? And that gets really quiet. Why? They don't know this answer very often. What's it going to cost to clean up the groundwater? Landfills will leak, maybe at some point, maybe past our lifetime. They might leak and get into the groundwater. Who's going to pay for that? Is that going to be paid for the $30 and $40 a ton? I don't believe so. It's an open question. The incineration, a similar situation. Look at some of the age of the facilities that are out there now. I know in Baltimore, I know in Saugus, Mass. There are some serious troubles with them. They're getting very old. They want to extend the life of them, but there are other alternatives. Siting a new one, forget it. Waste hierarchy, it's also down low, just above landfilling. And maybe, of course, no one wants a large stack in their backyard. I can understand that. The people in Baltimore have said, we don't want this polluter there. That's getting very subjective and finding out what's going on. People are complaining they're getting cancer. Maybe so from this. I don't know. I don't know all the facts. But if you have a polluter in there and emitting a lot of things, why not get rid of it as well? If you want to try and find a tried and proven alternative out there, you have to also answer these further questions. What current sustainable, future-oriented waste treatment and recycling practice and methods are being used now? What kind of technology is available out there? And what do I do with my organics and garbage? Okay, organics, garbage, nice juicy waste stuff. Of course, diverted from landfill. You can bring it to AD. There's some troubles in that too. We also have AD. InnoWaCon also has AD technology. What can be landfilled? What material can be landfilled? Maybe take a look at what Germany did. And what complementary technologies can be used are available there for use. And these questions have to be thoroughly addressed to come to a complete answer. Ideally, the complete solution is combining the waste collection, waste and recycling methods and centers that you have around. Just don't have a collector or a hauler out there bringing stuff to facility A, and they're not working together or working with the community together with a hauler, with a recycling center. If you can work together, you have much better cost control of things, and things can work much more efficiently. You have to have a sustainable waste treatment process itself out there, one that's really going to work and work for a long time. And all the products, the waste that comes off of this, you have to be able to utilize and recycle them if possible, and incorporate the complementary technologies where appropriate. Don't have to have a whole big thing that'll do everything from A to Z, but the appropriate things for your area. And it should be BAT. Everyone know BAT? BAT means best available technology. I believe people very often say state of the art and then also BAT. I believe they're two different things. State of the art, if you look at a timeline along my arm from here and going out into the future, state of the art, let's say it's right there. Okay, and time goes on and state of the art is still there. BAT is best available technology, and it makes iterations. It goes along with time. It's always improving itself and making itself better a long time. So it's always looking at new things, questioning if it's still viable and workable. One waste treatment solution that we've had is the mechanical biological waste treatment process, MBT. That exists, but they've had their own challenges and difficulties in the past. It's been shunned, yes, for some probably very good reasons. They have not addressed all the concerns that I've listed above in the last slides very often. They weren't complete systems. So I have an MBT that can do this, but it can't take everything else. But it'll do the job. We've seen that. It's difficult to control and maintain. There were 2 plants that were built in Heilbronn and Buchen in Germany with an MBT process that promised to do well and work correctly. It didn't. It didn't work at all. In fact, they tried to keep the process going. Pipes were getting clogged up, all sorts of troubles. They had to take these 2 MBTs completely down, demolish them, because this process did not work at the time. And that is a major thing with the MBTs because it's a mechanical, biological, thermal, chemical process that has to work together. They were in the past designed and built just enough to do the job, maybe not much more. And they didn't extract the maximum energy and value out of the waste as possible. Not sustainable, couldn't keep it going. And this resulted in unreliable plants. You just couldn't keep them running. Non-availability. You want a plant that you put a lot of money into to keep on running 24/7 or whatever your shift. And these weren't doing that. And facilities that look like this. And these are real pictures of a facility here. On the left side, you see the waste intake hall. Very dusty, very dirty on the floor. If you walk in there, very smelly. You don't see much sunlight coming through those windows. You're walking around with heavy shoes, okay, work shoes, safety shoes, of course, probably with a mask. On the right side picture, you're seeing the mechanical pre-treatment side of things with a transport belt on the lower left and open cable canals, cable troughs, where dust and whatever is flying inside of them, and OSHA and safety and fire safety, they're going to love this one because that's an accident waiting for a place to happen. Also looking at the biological drying step. These are tunnels. Each tunnel you see on the left side is around 5 meters wide, 5 meters tall, and 20, 30 meters long. You see all the air. Let's see if this thing works. Oh, let's go back one. Okay, you see all the smoke and air coming out of here, and very humid, very dusty, and not a nice place to work in. And I've seen people in similar tunnels like this, loading and unloading these tunnels. That guy was not a happy camper. He was doing it with a small front end loader, full gas mask. Because of that, he was hot and sweaty, and he wasn't happy. And he was very happy to finish shift and get home. And I'm sure they have a big turnover of people there. The other one is also a drying area, putting the stuff away out there to dry in a pile. That's a fire hazard out there. Also the tunnel area again, if you see on the right side toward the middle where that fog bank is hanging around and he's walking through it, probably very, very tasty. One of the doors is ajar. It's not working there. It's full of water and dust everywhere. Here, a lot of equipment is placed in a way such that you can't get to it, to a pump or a valve to fix it quickly if something breaks. There's also something lying on the floor. And of course, you have to have a shower station close by that you can't get to the pumps or whatever is behind it. Open composting with the smells. We don't have to talk about that because we've talked about that in the last couple of days. These problems were addressed and has resulted in MYT, maximum yield technology. This is an MBT technology that has really addressed all these problems and come up with something that is sustainable. It is tried and proven. The pictures you will see shortly, they're from a plant in Germany that has been, started in 2006, ramped up from May to August 2006, taking in 100,000 tons a year, has no downtime since then, is still operating, and they plan to go another 20 years on it. And the floors inside are as clean as the floor in this room right now, except in hall 1 where the waste comes in. You'll see that in a minute. It is a fully developed system, answering all the questions, what do we need? It is also flexible. Flexible, I mean, it is adjusted to the waste that's to come to it. For example, this little pointer here is a product, has a certain size, certain weight, can do certain things. A few buttons, fine. The MYT is a process that is flexible to the kind of waste that you have. So it's not just, oh, we just need that, that, and that. Rather, it can take the different ones. You just have to know what kind of waste you want to bring to it. Mostly MSW, but the content We have to know what it is and to be designed to fit the waste, not the other way around. Flexible with the inputs and also with the outputs. Biogas, RDF, refuse-derived fuels in different combinations can be worked out. It's also scalable. The minimum size is around 20,000 tons a year. And yes, we will come up to the number we heard yesterday, 300,000 tons a year is no trouble. 500, whatever you like. It can be expanded. At some point, there's economies of scale that you have such a large plant, it might make sense to split it and have two plants around a city, large municipality. So in case of some problems, there's always some redundancy somewhere. Make sense of the whole thing. It is a German technology, yes. It's available in North America now. We can have it. It can be brought over. Not the equipment, except for one piece essentially, but a lot can be bought locally, be it in US or Canada, it doesn't matter. A lot can be bought locally such that the companies that should supply pumps, material, transport belts can be qualified and they can be bought here locally, which makes a lot of sense. Buy USA, buy in Canada, good idea. MYT is not a product. MYT is BAT, B-A-T, best available technology now. Let's go through the process steps. We have waste acceptance, mechanical preparation, generally 5 steps, biological conversion, biological drying step, mechanical material separation. Let's look at each of these in a little bit of detail. How am I doing on time? Good, all right. Going from left to right, waste acceptance, where it comes in, and they first start to find out what I don't want into my system. So people have been known to put everything just perfectly into the waste bins, right? Into the bio bin as well, right? No. We found motor blocks, everything, guns, big stones, who knows what, everything can be found in the waste. And they take it out, the big stuff, they take it out in this section right here. Then the waste that we want goes along onto a transport belt, all enclosed. Why? We suction that air out of the enclosure. Also, the building's under negative pressure, so germs and dust and smells don't go out, rather fresh air comes in. Enclosed as well, we suction it out, so germs, animals, let's say birds, if you have different buildings, you will see we do have different buildings on the ZAC plant in Germany. Birds, animals don't come in, and also smells and dust does not come out. The rest of that good waste that we want goes into the mechanical pre-treatment section, where we take out different fuels, mostly RDF, a lot of plastics. And we know what we can do with plastics. We've talked about that in the last days. Minerals, meaning stone, sand, rocks, metals, and residual materials. This material then goes on to the biological step, the real heart of the system here, where we mix it in large mixers, very slow running mixers. Each one is around 4.5 meters in diameter. You'll see a picture, 20 meters long, and for about 2 to 3 days maximum retention time in these mixers, where we add processed water to it, not fresh water. Right now in California, in certain areas, it's very dear with fresh water. The waste coming in, because it has the biological or organic content in it, has a good water content. So you can use that processed water back in the system to mix. After a short time, those 2 or 3 days retention time, it comes to a press where we get the water coming off of here, and from the water side, we make the biogas, and we'll also get treated water. You'll see another slide, I'll go into that a little bit more. And the air coming off of here, we clean it in different ways. In Germany, we have to use an RTO, regenerative thermal oxidation unit, where it essentially burns the air, the polluted air, the heavily polluted air, at 825 degrees C before it discharges into the atmosphere, and constantly monitored, because Germany, they monitor every damn thing. Anyone been to Germany and know that about how they work? Yeah, everything's regulated. They'd even say in a conference like this, you just can't, you have to stop breathing for a few minutes because you're using too much air. That material, after 2 or 3 days after the press, as I said, the water side goes here, and the solid side after the press goes to the biological drying step. Let me go back. Biological drying step, which are tunnels. You saw those pictures of the other tunnels. These are all enclosed tunnels, 5 meters by 30 meters long, approximately. And the ZAC plant, taking the 100,000 tons a year, we have 9 of these tunnels. And the materials put in there, all enclosed. People are not putting it in front-end loaders, all automatically done and controlled. We put that material in there and we pump the hall air, the room air, through the material and suction it off from the upper side. And because there's a lot of organics on this material, it starts to decompose. After 4 days drying time, machine docks on, takes it to another empty tunnel and fills that tunnel for another 4 days. So after 2 times 4 days drying time, we have a material that's gone from about 40%, 45% wet to a maximum of 10% wet. A nice, dry, siftable material that you can take the stones and things out like that. This dry material then goes off to the mechanical material separation step, where we can get fuels RDF in different sizes. And I have some samples of RDF on my booth over here. When you come into the other room, you can see it on the left side, little jars. We can take a look at it. And there are some minerals, the sand and stones and porcelain chips. Hey, that can be landfilled. Why not? Nothing's going to happen to it. In Germany, we can landfill it. Maybe it can be used for underneath the base material for secondary roads. Or if the glass that comes out of it and the glass chips that come out here are really clean. And if glass becomes a commodity again, which maybe it should, but we'll see what the market does, you can sort that glass with glass sorters and take it out and bring it back into circular economy. Always a good idea. It's also the, is it worth it doing that and having the extra machines and extra people controlling these machines? And also we take out more metals from not only this side up here, but also metals here. Let's look at some of the inputs I said about flexibility. If you look at all of Germany, this box up here, this large box, this is the way they do it in Germany. It was talked about yesterday whether recycling, is it really correct or not? Mike was very adamant about it, Mike Hart, talking about things. In Germany, you'll have the gray bin, the organics bin, or they call it bio bin, with your nice juicy kitchen waste. You'll have the yellow sack where there's recyclable materials put in there, all your cartons, your yogurt tins, your yogurt plastic things are the hard plastics as well. They don't sort by 1 through 7s. They don't have that in Germany. They sort by the PP, PE, etc. There's a paper bin, very interesting. There's about 240 liter paper bin. It gets picked up every 3 weeks. And the paper company gets a fairly good quality paper so they can take it and make new paper, new cardboard out of it, used paper. And in town, you'll also find a glass bin where you can put your wine bottles, the other recyclable bottles that you don't reuse. There's also a lot of reusable bottles in Germany. Maybe we can back to that. Who remembers in the States, the beer bottles from Schlitz or whoever, Pabst, where pints come in and they're reusable. You'd bring them back. I remember those things from my dad. He used to have those. And that's, maybe we have to get back to that too, because it's been proven that it's a lot more economical. Yes, you have to bring them back. Yes, they have to go to washers and do this kind of thing, but I believe they've done the math on it. And if they get 35 to 50 cycles out, maybe a little bit longer, then it's good. So let's go through this a little bit quicker. Oh, important here. This is how they do it in Germany. Sack Kallenbach, we don't have the bio bin or organic bin We just have the gray bin. The organics are in the gray bin. So that's what they have at SAC. But MYT, if we know that you want to single stream it and have all that material come in there, it can be designed to take this material. This is what Hall 1 can look like. This is what it looks like at the SAC plant in Ringsheim, Germany, where I was working. It's fairly clean. Right now, you don't see the waste that's been dumped there, but it's cleaned every night. Mechanical pretreatment hall. It really looks like this. It's clean every day. And the young guys are taking care of this hall. This is the biological step. And in that biological step here, and important to know, that's the large mixer. Here's the press. The liquids go down to the fermenters, making the biogas and bringing the water back into the system. And the sludge, we don't have the sludge problem like they have with ADs, some ADs because of the material that they might get. The sludge goes into the biological drying step and ends up as RDF. Biological drying, the tunnels are on the other side, didn't show them there, but there's a tunnel extraction device that goes onto it. Mechanical material separation area. The outputs are biogas, typically 70 to 71% methane content. Use it correctly. Uniform production of CH4. That's very important. It's not spiked like that. It's around 7% of the original input. So we get 7,000 tons from the 100,000 tons we get at the ZAC plant. Utilized, converted to RNG, converted to diesel, SAF, sustainable aviation fuel. It's all possible these days with the complementary technologies. Also, green hydrogen. I venture to say it's green hydrogen, not gray, but we can discuss that. And thermally for electricity and heat. So you can burn it in a CHP. The outputs, the RDF, refuse-derived fuels. Very dry, 90%, and it's always that way. High calorific values, size dependent. Around 9,000, 22,000 kilojoules per kilogram, or I believe if my math is right, 3,900 to 9,500 BTUs per pound. Utilized as a renewable resource. In chemicals, RDF to methane processes, methanol process, sorry. SAF, sustainable aviation fuels. Thermally, in the cement industry, they like it because the chlorides are low, lower than 1%. Power plants can be co-burned with coal. Maybe that'd be going away in a little bit. RDF power plants as well. But please do not landfill. This stuff is too good to bury. Why landfill energy? Why landfill a resource? And they're doing that with MSW right now, landfilling a wonderful resource. Outputs are also metals, sorted by size, sold to scrap dealers. There's mineral stones and sand and glass. They're clean enough to landfill. As I said, you can also use them on roads. The glass, you can also sort it by color, bring it back, as we talked before, into the circular economy. There are plastics. We talked about that yesterday quite a bit. Yes, it is an enhanced MRF. Does a lot more. It takes it a lot further and completes the whole equation. They can be utilized and sorted by type into the circular economy, making new quality pellets, thermally utilized to burn. The processed water is in the biological conversion step and brought to the biogas fermenters. The treated processed water is reused in the process, in the MYT process, and does not use fresh water. I think there are more fresh water used in the toilets at the plant than they used in the system. It can be possibly used as a fertilizer and brought out into arid lands especially. And it is clean enough for the local sewage treatment plant to take on. Can be used in the chemicals to methanol processes as the water source and other things. Here's a breakdown of the 100,000 tons a year, what the sack plant in Germany gets. It might be different for another plant that'd be built, but similar. Cost to the citizens is very low. So let me put a number to that. For a 4-person household in the county, the Ortenau County in Germany, where I was living, it's 91 euros or about 110 bucks a year for the complete service, collection, processing at the plant, all the administrative, the paper pushers, the 20-odd recycling centers in the town, in the county. $110 a year. And the people get that bill once a year and they pay that. And what's very interesting about that is people are very conscious of what they're paying. And if they know what it is, they're going to say, well, what do I have to do to pay less? Well, maybe recycle or make less waste, which is a good idea anyway for the whole environment and economy and things like that. And I know some of the waste haulers and the large companies don't want to hear that because they like to make money off the waste. That's their job to do so, correct. But generally making less waste is much, much better. And you're modified, as I said, you're motivated to create less waste. We have some reference facilities, the one in Zach, at the Zach, the Zweckverband Abfallbehandlung Kahleberg, that's what it means, in Ringsheim, Germany. 100,000 tons a year since 2006. Simivad in Henny-Beaumont in France, 86,000 tons since 2015, all are running. In China, there's a small one that's been built. In the Onnut, Bangkok, Thailand, 300,000 tons a year since 2019, running very well. And the Thai waste is 70% wet. The waste flows out of the trucks. We designed it to fit that waste. And the more MYT plants in process. Do it right the first time. Use the correct MBT process out there. Get it right done the first time. Use MYT, truly viable and sustainable MBT process that does exist and is available now. It is reliable. High availability mean it's on, it's working for you all the time. We don't have any 2 weeks revision time, renovation time in the year. We do it maybe over the weekend. It is flexible, as we talked about, adaptable, scalable to the different sizes. It can be incorporated into the local waste regime you have now. You don't have to change everything up front to make this thing work. It is a safe and clean workplace, important these days. The regulations, wherever they are, can be upheld, and that's very important. Design it according also to the regulations that you have. And a high diversion from landfill, which everyone, not only California, wants, and in line with the circular economy. And costs are kept to the minimum. It's designed to fit, not too big, not too small. Thank you very much.
Thank you, Glenn. Very nice presentation. Do we have any questions? One question. Two questions.
Good morning. Number one, your assertion with regard to the gas concentration, the 70-71, is that are you saying that's for the system, or you're saying that that's what you have experienced at that location?
The gas that is produced at least at the SAC plant we have there, that is producing the biogas, it's 70-71% methane content all the time.
Okay, based on the general differential between waste stream content in Europe and the United States, would you expect there to be a different methane concentration in the US based on the different level of organics?
Could be. As I said, each plant is designed with everything in mind. Now, it is desired to have the organics come into it as well. So everyone is thinking, oh, you have to divert from landfill. Yes, the organics away from landfill, but why take it away from the waste? Why have an extra waste bin out there where you have to collect that? It's very smelly and miserable to work with. Have it in your waste bin and have that collected and brought there. So yes, you could probably have the same content.
Okay, I'm
possibly. I can't tell you right now because each MBT, each MYT, maximum yield technology MBT, will be built to fit the waste that is coming to it, designed to fit.
Oh, okay, that makes sense.
Okay.
And then the last question is, the little box on your flow chart with regard to, you went down and you had water and you had, methane out and gas out. Could you just speak to the actual process that's happening in that flow chart box a little more? I mean, is there heat applied, or what is the mechanical associations actually occurring in that area?
Okay, in that biological conversion step, that's I think where you mean,
Yes.
and the box below. Biological conversion, I have to do it quick because we get to the next one. And we can talk about that also a little bit later, but it's taking that waste, mixing it with the water, slowly mixing it. No gas is produced there. It just comes to a press, and the liquids go to the fermenters, making the biogas. The solids go to the biological drying step. It's fermenting, the liquids are fermenting, and has a lot of the organics in it, making the biogas. Material is not fermenting, you're not doing that, so you have a lower TS content in there because you don't have that heavy material in there. You're not biogassing the material itself, the waste itself, just the liquid side. Yes, it has sludge in there too, but we take care of that.
I know we have two more questions, but I'm going to ask to hold them off towards the end of the session. I want to be respectful towards our second speaker. I think we will have some time at the end. We can roll over to the break.
And I can also meet you at the booth out here. Thank you.
Thank you. Our second speaker is Dr. Hao Kai from the Argonne National Lab. And he will talk to us about the waste to diesel conversion, specifically about the DOE's initiative called Co-Optima. It's always nice to hear the perspective of someone from Washington, from the federal agency. It's nice to hear which direction they are pointing us in. Dr. Kai, can you hear us?
Yeah, I can hear you. Can you hear me?
Okay, the floor is yours.
Okay, thank you. Yeah, first of all, I would like to clarify I cannot represent Washington or DOE. I'm just a researcher from Argonne, but our work is funded by DOE. So here I'm pretty happy to present some recent work on life cycle analysis, looking at renewable diesel fuel that could be produced from wet waste feedstocks for Co-Optima heavy-duty vehicle applications. So for some of you who may have known the Co-Optima program under DOE, it has been running for about 6 years now. The first 3-4 years has been focusing on developing fuel technology and engine technology for light-duty vehicles. And in the recent couple of years, we have been switching gear to look at fuel and engine technologies for the heavy-duty vehicle technologies. So the overall objective of Co-Optima is try to really develop cost-effective fuel technologies that could be produced from alternative feedstock other than fossil feedstock in a conventional way, and therefore offer low carbon performance and hopefully performance enhancing or engine efficiency enhancing properties for light-duty vehicles or emission reduction benefit for heavy-duty vehicles. So here I'm focusing on the work looking at alternative renewable diesel fuel that could be produced from wet waste feedstocks, again, for heavy-duty vehicles, coupled with some Co-Optima engine technologies, such as ducted fuel injection technologies, that could tremendously reduce the engine out NOx emissions or particulate matter emissions, which are conventionally critical challenges for heavy-duty engines because of the stringent emission standard in the US and across the globe. So here, again, we have been exploring different feedstock types or resources that could be used to produce hydrocarbon dropping renewable fuels, including renewable gasoline and renewable diesel fuels. Here I'm going to focus on the effort to look at some of the waste resources out there in the US to produce functionally tangible fuel that could be blended with conventional petroleum diesel fuel. in the refinery or for co-processing. And we are here to produce some life cycle analysis to inform the R&D through both life cycle analysis and techno-economic analysis, which has been done by some partners from other national labs, including National Renewable Energy Lab, Pacific Northwest National Lab. I was going to focus our work on the life cycle analysis here. And at this moment, we have just submitted this work to a journal article. So hopefully in the not so distant future, we could have this work published in the public domain. In this particular analysis, we have been looking at initially a wide range of wet waste feedstocks out there in the US based upon some resource assessment studies conducted by our NREL colleague. And here we are focusing on two types of wet waste feedstocks, including animal manure, in particular swine manure in this particular analysis. And the other one is the yellow grease, but based upon the feedstock availability as well as the potential to produce renewable energy for this waste feedstocks. The first technology we have been evaluating here utilizes yellow grease as a feedstock, which goes through the hydrogelation, hydrocracking, hydroisomerization, or the entire HERFA process to produce intermediates such as alkanes, isomers that could be hydrotreated and converted into a range of renewable hydrocarbon fuels, including renewable diesel. So we have been looking at the resource availability to size the biorefinery in our modeling work. We have also tried to look at the potential impact of the feedstock composition on the conversion performance, and also from both the economical and the environmental analysis standpoint, we vary the size of the plants to look at the impact on the sustainability and the cost performances. The second technology we look at here is to produce renewable diesel fuel with swine manure that could be go through the hydrothermal liquefaction or HTL technology to produce renewable dropping renewable diesel fuel. And with this technology, we have been focusing on the potential benefit of generating high yield of biocrude through the HTL process, which could be account for about 50% of the carbon conversion efficiency. This HTL biocrude could be converted to diesel fuel through some followed hydrotreating process. And overall, the diesel cost could account for about 60% or more, which presents a good renewable diesel yield through this technology. And on the quality side, this HTL pathway could produce high cetane diesel fuel among other favorable properties that could enable reducing engine out air pollutant emissions, coupled with all the Co-Optima technology, as I mentioned, for example, ducted fuel injection technology. For this particular one, here is the system boundary or the scope of the LC analysis, where we look at a decoupled HTL plant that's assumed to take about 110 dry ton per day, the swine manure, and convert that to the biocrude. And the biocrude will go through a hydrotreating upgrading process to produce the finished product. And here is in our life cycle analysis what we considered, which highlighted two major supply chain. One is representing the conventional waste management practices, which we call the business as usual counterfactual scenario, which is being avoided since the waste would be shifted or diverted from this business as usual practices to the bioenergy production scenario. And we take into account of what would be avoided or foregone because of this diversion. And in the bioenergy production supply chain, we start with look at the waste collection, transportation, and going through the conversion process at the biorefinery to produce a renewable diesel fuel. The analysis work is done by the greenhouse gas regulated emission and energy use in the transportation model, or known as a GRID model, which we developed at Argonne National Lab with support of multi-transportation offices of the ERG, DOE, in the past over 2 decades. So here we utilize mostly the fuel cycle, the GRID 1 model, to do the well-to-wells life cycle analysis. Here with this effort and other parallel waste-to-energy, waste-to-product life cycle analysis that we have been doing here in our group, where we are developing a new waste management and waste-to-energy, waste-to-product module within the GRID model, which is incorporated into the upcoming new version of the GRID model that's going to come out in a couple months. So jump to the results. Here we show the life cycle greenhouse gas emissions of renewable diesel fuel, or we call them mixing control compression ignition, or MCCI fuel for Co-Optima context. We see here the yellow grease HERFA conversion route could produce fuels that offer about 11 grams per megajoule carbon intensity. This represents about 87% emission reduction compared to the petroleum diesel, and could potentially be produced at around $4.40 per gallon gasoline equivalent at the current state of technology, or could be eventually lowered through some larger scale production or continuous improvement of the conversion technology. For the swine manure pathway, we look at actually negative carbon intensity, mostly be attributed by avoided methane emissions during the waste management. We also consider some foregone carbon sequestration credit of the otherwise non-filled AD digestate of the manure to the soil for application, or for fertilizer displacement. Overall, this pathway could potentially offer more than 100% of the emission reduction compared to the petroleum diesel pathway. And the production cost is estimated to be about $3.60 per GGE. And if we could scale it up to about 250 tons per day, the estimate through our process modeling and the TA work suggested the minimum fuel selling price could drop to about $3.10 per GGE. We also conducted some sensitivity analysis to try to understand what could be the key drivers for the carbon intensity for the fuels. Here we take the swine manure as an example. There are 2 major things we are evaluating here. One is look at the impact of the feedstock quality, look at the ash content and the solid content, and how they impact the overall carbon intensity. So here, as we could say, higher ash content could actually penalize the carbon intensity because it reduces how much methane emissions that could have been avoided, because the high ash actually would lower the biofuel yield and eventually penalize or increase the carbon intensity at the same time. Same thing could be said to the other quality attributes of the feedstock, that is solid content for this waste resource for the similar reasons. And at the same time, we will look at the impact of the conversion performance, especially the conversion yield at both the HTO plant and eventually the hydrotreating step. The impact is a little bit counterintuitive here. Basically, the higher the conversion yield or efficiency, the higher the carbon intensity for this particular case. The major reason is a potential trade-off between the higher yield, which reduce the direct emissions during the conversion step, is basically outweighed by the lowered or reduced avoided counterfactual scenario emission credits. Because the higher conversion efficiency, which means it takes less amount of wet waste feedstock to produce the same to produce a megajoule of fuel, and that translates to a less amount of avoided methane emission that being given as a credit to the finished renewable diesel fuel pathway. We also look at a couple of alternative counterfactual scenarios that could be considered as possible for swine manure. Other than the traditional AD process followed by landfill or soil application route that we consider in the base case, we also look at another two cases where either the biogas during the conventional AD process, conventional landfill and land application process, which generate a lot of methane emissions, and if that all of those methane emissions get flared, we look at somewhat increased carbon intensity compared to the base case, which is solely attributed to a reduced amount of the avoided methane emission credit. The other sensitivity case we look at is if the manure goes through the AD process for power generation, and that power could displace or get exported to the grid and displace the conventional electricity grid in the US. This represents essentially competing technology to shifting the swine manure for renewable diesel production. And in this particular case, we look at some foregone electricity displacement credit from using the AD biogas for the power generation. And therefore, the carbon intensity of producing renewable diesel with swine manure compared to this counterfactual scenario will be much higher, which is about 70 grams per megajoule. With both the TE and ILC results, we looked at another dimension of the technology by assessing the marginal GHG emission abatement cost, or the MAC, for both technologies here. We look at the swine manure via the hydrothermal liquefaction route. We estimated the MAC to be around $500 to $100 per ton of CO2 emission equivalent reduction, which vary as a function of the fuel price of the conventional diesel fuel, and also very depending on how we assume the counterfactual scenario impact, or which affect the carbon intensity of this technology, as well as the plant size, the potential economic of scale, and other conversion performances. So this can compare to the cellulosic ethanol technology, and which was estimated to have about $50 to $375 per ton of greenhouse gas emission reduction at the current cellulosic ethanol production technology and their carbon intensity. And for the yellow grease conversion technology, we look at a mark of about $100 to $250 per ton of GHG emission reduction. This is without considering the likely low carbon fuel standard carbon credit that's already being in effect because of the California and adjacent carbon market for renewable diesel fuels. If we consider the carbon credit, which is about $180, I think, at this moment, we could essentially be expecting near zero marginal emission reduction cost for producing renewable diesel with the yellow grease. And we also generate results for fossil energy and NOx emissions. Generally, the benefit of fossil energy reduction much smaller for example, the manure HTL pathway, which does not get much benefit from avoiding some counterfactual scenario consequences, as we do see from the GHG emission analysis. And for NOx emissions, we see the swine manure one could all actually exceed the performance of the petroleum diesel, mostly as a combination of fuel combustion, fuel production, as well as some avoided or foregone emission credits in the counterfactual scenario. And here is a comparison of some of the broader metrics we developed for the Co-Optima fuels, looking at the technological readiness levels, economic viability, and environmental. So overall, these two waste conversion technology are pretty promising, despite some challenges. For example, some testing or certification procedures still need to be completed. There's some scalability issue because of the availability of the waste feedstock. So the key takeaway here is through this LC and actually the companion TA, we found that no carbon fuels could be produced from waste feedstocks at near competitive prices, which could be used for diesel fuels. And despite the challenge of decarbonize the heavy-duty transportation sector, such no carbon fuels could offer a path forward to achieve this goal with favorable marginal emission abatement cost. Finally, I would like to mention that the work is ongoing and getting wrapped up for Co-Optima, but there are other ongoing DOE programs looking at, for example, the sustainable aviation fuel, marine fuel that could be produced with waste feedstock, including wet waste, waste CO2, and as well as MSW. So there's still a lot of ongoing effort look at the broader waste to energy space at this moment. Finally, I would like to acknowledge my colleagues who has been contributing to this work. So with that, I stop here and happy to take any question you may have. Thank you.
Thank you very much. Thank you very much, Dr. Kai. Do we have any questions? Okay. Thank you again, Dr. Kai. We have a couple of minutes left, so perhaps we can return to questions for Glen. I know there are two questions from this side of the room. You can use this mic. So go ahead.
Opine on the CapEx, OpEx. I know you said it was about $110 per family, but that's not how we do it in the United States. So is your OpEx and CapEx based on tip fees and then sale of off products? That's the first question. And the second question is, do you have any active permits in the United States? Because essentially you are a MRF. So to say that it's hard to permit a landfill. It's also extremely hard to permit a MRF at this point in the United States. However, in the Southeast, there are over 125 active landfill permits in the EPA. So how do you defend that statement also?
Well, one, I can say, I don't consider this MBT as a MRF. It's enhanced MRF, if you will. Receiving waste, but it's not a MRF. And they'll look at it a different way because it really is another technology, but I'm not going to try to argue with the EPA, try to also work with them on things like that. With the costs, this 91 euros or $110 a ton is what it costs a 4-person household. The ZAC in Germany is a nonprofit. It belongs to the community. So it is not allowed to make a profit. It belongs to the 2 counties we belong to. So whatever costs we have, we give it back to the citizens. It used to be 96 euros for a 4-person household. We made some more efficiencies in the whole thing, brought down to 91. So if we were to rebuild this plant right now, according to MYT, because it was built before, let's say, MYT was finalized, it was just an MBT called the ZAC process, it would cost us around 60 million euros for this 100,000 ton plant. That is based on German costs, labor, material, insurance, the whole shebang, permitting and all that, okay? One thing with permitting in Germany, you have to fill out, it's called the BIMSCH, Bundesemissionsschutzgesetz. You have to fill out a certain form for that kind of facility that you have. And once you put all the things in and they are accepted, they have to approve it. If everything's okay, I know it's different in the States and it doesn't work that way here, right? And talking to people saying in California, also at another conference, saying permitting takes years because it has to go to this one, this guy. It's like going upstairs to get form number B, but you have to go down in the cellar to get form number C and go all over the place to do it. It's done different in Germany. Okay, we're not Germany here, I understand that. We have to work with it to find it out. And you could put this kind of facility, this non-MRF, enhanced MRF, on a landfill site and take over this, not over the landfill material. We're not talking about landfill mining, rather fresh waste. Possibly it could be enhanced to do landfill mining, but who knows what's really down in there. It's not just fresh MSW. So different ways to do it, and opening up landfills again, then you're talking about serious odor problems out in the area. I've seen that done in Switzerland.
One more question,
All right, hang on.
then we'll take a break.
Yeah, so you mentioned the biogas is 70% methane, but you didn't mention how many BTUs you get out of per ton, or what's the production of that biomethane, what do you get out of it?
Well, the methane with 70% methane content in the biogas, I don't know the BTUs of methane itself. That's CH4, pure CH4.
No, I mean per ton of processed waste.
We get 7,000 tons, about at this ACT plant, 7,000 tons of biogas for the 100,000 tons of waste. Okay, you can do the math on that. I don't know that right now, but 7,000 tons, what's that, 7 million norm cubic meters, something like that. It's 1.01, I think. So that's quite a bit.
One last question. Okay.
Yep.
Thank you very much for your attention. Dr. Kai, Glenn, thank you for your wonderful presentations. We have about 25-minute break right now in the exhibit hall, and we'll reconvene here at 10:30 for the last session. Thank you.
We can also ask more questions if you have at the booth over there, and as well as all the other exhibitors that we have there too.